Hey everyone, today we are going to talk about probability. The first page of your notes is a list of vocabulary. We're going to talk about the vocabulary quickly, but we'll get into it more during the notes. So just take a moment and copy this vocabulary. I will read it, and if you need to pause the video to jot it all down, that's something you can do. Probability, the likelihood of an event occurring. Trial, one single attempt or repetition of an experiment. Frequency, the number of times an outcome occurs. Sample space is the set of all possible outcomes. Experimental probability is the probability based on what actually happens when you do an experiment. Theoretical probability is the probability based on what should happen using math. Lastly, compound event, an event in which two or more outcomes can occur at the same time. Let's look at the probability number line. This number line is going to go from 0 to 1. So let's write that down here on this number line, which means that 1/2 is going to be here in the middle. We need to use these words to place them on this number line to explain what each of these numbers mean in probability. Let's start with 0. If something has 0 probability, then it is going to be impossible for that thing to happen. For example, you could say the probability that my cat is going to have wings is 0. That would be impossible. Let's do 1. 1 means that something is certain to happen. Maybe the probability tomorrow that it is going to rain is 1, meaning it's certain that it is going to rain tomorrow. Let's talk about what's in the middle. In the middle, it's going to be equally likely or unlikely. And that leads more likely and less likely left. So more likely is going to be between 1/2 and 1, and less likely is going to be between 0 and 1/2. Okay, let's look at this review. The probability of an event can be calculated using the following formula. So the probability of event is going to be desired outcomes over total possible outcomes. A bag contains 3 red marbles, 2 blue marbles, and 5 green marbles. The probability of choosing 1 red marble out of the bag is, so we are going to use this formula to determine this probability. So the desired outcome is going to be a red marble, and there are going to be 3 red marbles. There are 3 possible red marbles that I could choose. So that number will be in the numerator. And my total possible outcomes is the sum of all the marbles. So 3 plus 2 plus 5, meaning there are 10 different marbles that I could possibly choose out of the bag. So as a fraction, the probability is 3/10. You replace the marble you choose and choose another marble. The probability of choosing a blue marble, now my desired outcome is blue. So I have 2 possible blue marbles that I can choose, but my total possible outcome stays the same at 10. This one can actually be reduced to 1/5. Let's go on to this spinner. We're going to use this spinner right here to answer these following questions. The probability of spinning a 1 is, so there's only one 1 that I can spin out of how many different possible outcomes? 1, 2, 3, 4, so 1/4. The probability of spinning an even number, well, an even can be a 2 or a 4. So the probability of spinning one of those is 2 out of my total possible outcomes, 4, which can be reduced to 1/2. The probability of spinning a number less than 4, which would be 3, 2, or 1. So there are 3 possible outcomes with the same number of total possible. The probability of spinning a 5. So if you look at the spinner, it is going to be impossible to spin a 5. So that's going to be 0. The next page. Let's apply this concept of probabilities to make predictions. Using this same spinner right here, explain why the probability of spinning an even number is 50%. So there are 2 even numbers and 4 possible outcomes, which is going to give me a probability of 2/4, which is the same as 50%. Blank probability is what is expected to happen. In this case, with the spinner, the theoretical probability of spinning an even number is 50%. Okay, so mathematically we calculated that it should be 50%. That is called theoretical probability. That is what mathematically is supposed to happen. Let's contrast that with what actually happens. Blank probability is what actually happens and is determined through observations. So that is called experimental probability. That is what, when I spin a spinner, 50% of the time I may get an even number or I may not get an even number. If you were to spin the spinner 10 times, you should expect to spin, okay, so if it's 50%, I would expect to spin 5 even numbers. Mathematically, that is what is supposed to happen. Do you think you will? Explain why or why not. Well, I could spin 5 even numbers, but the number of trials is so low that it's likely that I may not spin exactly 5 numbers. If you were to spin the spinner 100 times, you should expect to spin 50 even numbers, exactly half of 100. Do you think you will? My number of trials is increasing, which means I'm going to be closer to my theoretical probability, but it may still not be exactly 50. If you were to spin the spinner 1,000 times, you should expect to spin how many even numbers? Again, 50% is going to be 500. Do you think you will? Explain why or why not. Well, my number of trials is increasing, so I am going to get closer and closer to my theoretical probability. Am I going to get exactly 500? Probably not, but should be closer. Let's read this statement down here that's in a box. It says, as more trials are completed, experimental probability tends to approach the theoretical probability. This is a very important concept. Theoretical probability is what mathematically should happen. Experimental probability is what actually does happen. As you do more and more trials, they are going to get closer and closer together, meaning the experimental probability is going to be closer and closer to the theoretical probability. In the real world, probabilities are often used to make predictions. Data is collected over time, and the experimental probability is calculated. Let's look at the following table as an example. So this is the probability of being in a car crash during each month. This is something they have already calculated using experimental probability. Okay, so you can see the numbers there. The sum of the probabilities in this table is, now we can take a minute and sum them all up, but if I sum them all up, it's going to give me 1. The sum of all probabilities will always be 1 because it is certain you will get an outcome from all possible outcomes. So my car crash is always going to occur in a month. There's never going to be a car crash that doesn't occur in a month. Let's use the data to make predictions. Out of 200,000 crashes, let's predict how many of these occurred in January. We can use our probability formula, which is the probability of an event equals desired outcomes over total possible outcomes. I know that the probability of getting into a crash in January is 0.077, and I get that from right here on this table. So the probability is 0.077. I don't know how many of those are in January. That's what I'm trying to figure out. I don't know the outcomes in January, but I do know that the total possible outcomes is 200,000. So that goes in my denominator. Now I'm going to use my algebra to figure out my x. I can multiply each side by 200,000. Those will cancel out, and so I get x equals 200,000 times 0.077, and doing the math, I get 15,400. Out of 200,000 crashes, predict how many of these occurred in May. So let's use the similar example from above. So the probability in May is 0.091. That is equal to however many crashes occurred in May, which I don't know, over 200,000 total crashes. Now to solve for x, I'm going to multiply each side by 200,000. Cross out over here. The probability in May is going to be 0.091 times 200,000, which will give me 18,200 crashes. Okay, the last page of the notes, we're going to talk about compound events and also sample space. So remember, sample space is the total possible outcomes. If I flip a coin, the possible outcome would be heads and tails. Now, however, let's say I flipped a coin 2 times. One great way to do this is to make a table and list your possible outcomes. So if I flip it once, my possible outcomes are heads and tails. And if I flip it again, my possible outcomes are heads and tails. So I could have, I'm combining my rows and columns here, I could have a heads and a heads. I could have a tails and a heads. I could have a heads and then a tails, or I could have a tails and a tails. So my sample space would be a heads heads, a tails head, a heads tail, or a tail and a tail. Another way that you can do this, I'm just going to quickly show this other way, is you can make a tree diagram. So if I flip a coin, my options are getting a heads or a tail. If I get a heads, then I could get another heads, or I could get a tail. If I get a tail, I could get a heads next, or I can get a tails next. So then you're going to follow the branches to see your sample space. So I could get a heads heads, heads tail, tail heads, or tail tail. A coin is flipped 2 times. The probability of the coin landing on heads both times is, so we go up and look at our sample space. I can get a heads heads 1 time. That's only one option. And how many total options are there? 4. So it's going to be 1/4. Because heads heads is one outcome of 4 possible outcomes. The probability of the coin landing on tails both times is, so let's look at our sample space right here. So that would be a tails tails. Well, there's only one of those and still 4 possible outcomes. So also going to be 1/4, or we could also write 25 hundredths, or you can even write that as a percent. The probability of the coin landing on one head and one tail in any order. So it doesn't matter if I get a heads and then a tails, or a tails and then a heads. So if we look at our sample space, there's 2 of them, this one right here, tails head and heads tails, that are possible. So there's 2 possible out of 4 total. So 2/4, which is the same as 5/10, or you could also write 50%. The probability of landing on heads then landing on tails. So in that case, I have to get a heads first and then a tails. So it would be this one. That's only 1 possible out of 4 total. 1/4. Or again, you could write 25 hundredths. Now determine the sample space for flipping the coin 3 times. Justify your reasoning in an organized way. We are going to do a tree diagram again. If I flip a coin 1 time, I can get a heads or I can get a tails. If I flip it a second time, on the heads, I can either get a heads or I can get a tails. Same thing down here. If I flip a tails first, on the second one, I can get a heads or I can get a tails. Going back to the top here, if I get a heads first and then the heads second, my third flip can either be a heads or it can be a tails. If I get a heads first and then a tails second, my third flip can either be a heads or it can be a tails. If I get a tails first and then a heads, my next flip can again be a heads or a tails. And then if I get a tails and then a tails, again, my third flip can either be a heads or a tails. And now as you can see, doing it like this is great, but once you get various trials, it can get a little bit messy. So do your best to keep it organized. Let's write down the sample space here following this diagram. The sample space comes from following the branches. So I have heads, 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 tails, heads, heads, tail, heads, heads, tail, tails, tails, head, head, tails, head, tail, tails, tails, head, and tails, tails, tails. Calculate the following probabilities flipping a coin 3 times. Order does not matter for numbers 1, 2, or 3. Order does matter for number 4. So the question's asking me on number 1. It's saying the probability of getting a heads, heads, and tails. Remember, order does not matter. So that means just any 2 heads and 1 tail. So here's 2 heads here, 2 heads here, and 2 heads here. So that is 3 different ways I can get 2 heads and 1 tail out of my total sample space, which if I count them is 8. And I can reduce that to a decimal as well. Number 2, probability of getting 3 heads. There's only one way to get 3 heads. So that's going to be 1 and the same sample space, 1/8. You can reduce that to, or change that to a decimal, 0.125. Okay, third one, 2 tails and 1 head. Order doesn't matter. 2 tails, 1 head, 2 tails, 1 head, 2 tails, 1 head. The probability would be 3/8 as a decimal, 375 thousandths. Number 4, order does matter on this one. I have to get a head, then I have to get a tail, then I have to get a head. So that's right here. That's only one way. A head, a tail, and a head. So that's going to be 1 out of 8, which is 0.125 thousandths. Okay, that's it for today.